Everybody? So this is the last lecture that's specifically on generics, and then we'll move on to, we're going to go back to looking at some lists and list algorithms in the next lecture, and then I guess next week we'll look at some of the old exams. Okay, so I'm going to start by talking very briefly about sorting. Right? So you know from 121 that sorting is it's one of the fundamental problems in computing science. Right? So sorting algorithms are always studied by computing science students in first year or second year. There's many types of sorting algorithms. So the sorting algorithms you were probably taught in 121, they all had something in common, which I'll get to in a moment. Right? You probably also learned about binary search, right? So how to search a sorted array or list. Right? And then there's many data structures that rely on sorting. So for example, tree sets in Java are sorted sets, right? And tree maps in Java are maps where the keys are sorted, right? If you've looked at your current assignment, then you know you have to implement a sorted map as well, so a small map. In 235, you'll learn about search trees. So these are data structures that can perform efficient search. They're how sorted sets and maps are implemented. They're one of the ways that sorted sets and maps are implemented. So we looked at a queue in the course, right? So remember, a queue is just a sequence of items where the first item in the queue is the first item out. There's a variation of a queue called a priority queue where each item gets a priority. So the item with the highest priority is the first one that comes out. And so these are useful in a lot of places and in a lot of computing science algorithms, right? And so on and so on and so on. So sorting is really useful. Okay, so the sorting algorithms you were taught in 121, they all had one common mathematical operation, right? And that was, so how did you sort stuff in 121? Anybody? They all relied on one particular operator. Yeah. Yeah, you have to be able to do less than or greater than, right, to sort. And so these are called comparison-based sorting algorithms. I suspect you'll never see them, but there are ways to sort without doing comparisons. So those are called non-comparison-based sorting algorithms, but they don't work in. They don't solve the general sorting problem. So to solve the general sorting problem, you have to compare. Right? Now, if you wanted to implement, say, a sorted set or a sorted map in Java, right, you have to be able to compare elements. So is there some way that you can impose this constraint on the generic type? Right? The answer is there has to be some way to do this. Right? Otherwise, you couldn't implement these collections in Java. Right? And so the solution in Java is to use what's called a bounded type parameter. Right? So when you need to restrict the type that your generic type can take on, you want to use a bounded type parameter. Right? So the way you do this is you use the keyword extends. Right? So again, notice Java, like many other languages, likes to recycle its keywords. Right? So here extends now has a second meaning. Right? So extends for us means you create a subclass. But now it also means you can create a bounded type parameter with this keyword. So you use extends after the type parameter followed by the upper bound. Right? And so I'll explain what that means in just a second. Right? Your upper bound can be one of two things. So it can be a class. Oh, there's an F missing here. That is a descendant. So the upper bound can be a class that the type is a descendant of. I guess I'll fix that right now. Otherwise, it's very confusing. Right? Or it can be an interface that the type implements. Right? So it's easier to understand with an example. Okay, so remember our point2 class. Right? So our point2 class has two coordinates x and y, and they're both of type double. Right? But there's many applications where you want a point2 object, where you want a coordinate, sorry, and its coordinates are not necessarily of type double. Right? So you might want integer coordinates. If you're implementing, a lot of games use character-based coordinates, right? So A, B, C, D, E, F, G, and so on, and so on, and so on, and so forth. Right? And so why don't we take our point class and make it generic on its coordinate type? Right? Well, to just change the fields, it's very easy to do. Right? So we can do the following. Right? So I can make the class, so we can change our type double, right, and make it generic, right, by adding in a generic type parameter here, right? So now we have a point 2 class where at least the field can have any type, right? And that's the problem here, right? So now our coordinates can have any type, but that doesn't really make sense, right? So it doesn't really make sense if your coordinates are strings, it doesn't make sense if they're dates, and so on and so on and so forth, right? So what we'd really like to do here probably is to restrict T, or the types that T can have, so that they are numeric types, right? So the way you do that is you introduce a bounded type parameter, like so. Right? So now inside the angled brackets, right, if you want to impose a constraint on T, you can say that T extends number, right? And this means that T can be any type as long as it's a subclass of number, right? And so the number is called the upper bound, right? So if you think of the upper bound, so if you think of drawing the inheritance hierarchy for the number type, right, then number would be at the top of the picture, right? Thus it's the upper bound. Right, so number is the superclass of the classes big I integer, big D double, big C character, and so on and so on and so forth. Right, so it's the supertype for all of the wrapper types, all of the numeric wrapper types in Java. Right, and so now you can make a point 2 whose coordinates are integer, or a point 2 whose coordinates are double, or float, or long, or whatever else you like, as long as they all extend the number class. Right. Now, when you extend something here, so when you introduce a bounded type parameter, the number, that thing there, doesn't have to be a class. Right? It can also be an interface. Right? So in your assignment, you're implementing this thing called sorted minimap. Right? Now the assignment doesn't do what I'm about to show you. It does it a different way. Right? But in a sorted minimap, the keys are sorted. Right? So you want the keys to be comparable, right? And so you can impose that constraint if you wanted to, right? So here we say K extends comparable K, right? And what does that mean? It means that your key type, right, can be any type as long as it implements the comparable interface. So now I can use any type of key as long as we can compare keys using the compare to method. Right, now the assignment does this in a different way, right? So the assignment doesn't add this constraint. Instead, the constructor takes in an object that knows how to compare two keys, right? And then you use the object to compare the keys. So there is another way to do this. And in fact, the standard library classes, so treeset and tree map, they use a combination of the two techniques. Either the key is comparable, or you provide an object that can compare two keys. Right. Okay, so you can have a method that also has bounded type parameters, right? So it doesn't have to be a class, right? You can also create generic methods, and the generic methods themselves can have bounded parameters. Right. So here's the method count greater than. So it takes in okay, so it's going to count the number of elements in this array that are greater than that value, right? So it's already generic, right? So our array type is generic, our element type is generic, right? So to implement the algorithm, it's easy to do, right? You just loop over the array, you look at each element in the array, and you ask, is it greater than elem, right? And if it is, you add 1 to the count, right? So what you want to be able to write is the following, right? You want the count to be 0, you want to loop over the array, and then you want to ask the question, is E greater than elem? Right? But you can't do that, right? Because the greater than operator is not defined for reference types in Java. Right? So what do you need to do instead? You need to use compare to. Right? You can only use compare to as long as T implements the comparable interface. Right? Not all types implement comparable. So if you use some array type where the type doesn't implement comparable, you're kind of stuck. Right? But if you impose the constraint that T implements the comparable interface, right, then you can use compare to here, and away you go, right, and everything's fine. So again, notice here, the keyword is always extends, even though that's an interface. right? So when you have a class that implements an interface, the keyword is implements. When you want to restrict or bound a generic type, the keyword is extends. Right. Right. Any questions so far? So that's a bounded. That's imposing a bound or an upper bound on a type parameter. Okay. So what else can you do? All right. So remember when we were talking about a generic array-based list, right, or stack. I don't remember which. Right. I told you that arrays are covariant in Java, but generics are invariant. Right. And so what that means is if you have a list of string, right, that's not a subclass of a list of object, right? Even though string is a subclass of object, right? So string and object are related via inheritance, right? String is an object. Right? The same is not true when you use string and object as generic types, right? So in other words, a list of string is not a list of object, right? That's why there's that big X here, right? If you try to make, so if you make a list of strings here, and you try to store that, or you try to make, you make a list of objects, and you try to store a reference to that list of strings, it doesn't work, right? If you made a string, S, and then you made an object, O, you could write O equals S. Right? But when these things are generic, when these things are lists, that doesn't work anymore. Right? Now there's a good reason for this, which I never did tell you about back when we first discussed this. Right? So suppose that a list of string was a subtype of list of object. Right? So in other words, imagine that this picture on the right was actually correct. Right? So you could substitute a list of string for a list of object. Then you could do the following. Right? You could write, you can make a list of strings. Right? So here I'm going to make an array list. Right? Now I'm going to make a list of objects, and I'm going to say objs equals strings. Now remember what that does in Java, right? So that says that objs is the same list object as strings. Right? It doesn't make a new list. It just says that objs is now the same list that strings is. Right? Now you can go ahead and use objs to add any object, right? Because that's what you just said here, right? So objs is a list of any object type. So I can add whatever object type I want to that list, right? And now, when I go to get the first element out of strings, right, it's no longer a string. It's actually a date, right? And so now you run into problems like this, which you don't want, right? The whole point of generics was that they're supposed to be type safe, right? I shouldn't be able to put a date object into a list of strings, right? But if generics were covariant, then you would be able to do this sort of thing, right? And so the language designers decided this was not a good thing, and they didn't allow this to happen. Okay, so does that mean that if you have a generic type, that you can't make subtypes that are also generic? And the answer is no, right? So you might be concerned here, well, if list of string is not a subtype of list of object, can I still use generic types in inheritance, right? And the answer is yes, right? So if you have a generic class and you extend it, right, so you make a subtype, then you actually create a generic subtype, right? So you're in assignment, you've got something called an abstract minimap, right? So this is just a map that has some key type and some value type, right? It's called a minimap because they're supposed to be small, right? And then the assignment says a sorted minimap, right, inherits from abstract minimap, right? And so that actually creates a new generic type, right? That one right there, that is a subclass of abstract minimap, right? And so what does that mean? That means you can write abstract minimap m equals new sorted minimap, and that works just fine. Right? Set is, the set and sorted set interface are related. It's not exactly inheritance, but the set interface is called is a sub interface of sorted set. Right? So in other words, every sorted set is also a set. Right? And so sorted set is a generic subtype of set. Right? So if you extend a generic interface, you end up with a new generic interface that is also a subtype. Right, so you can still use generic types in inheritance. Okay, so one more thing that you can do. So if you make a generic class that implements a generic interface is also a subtype. Right? So tree set actually implements this sorted set interface. And so every tree set is a sorted set. Right? So I can make a tree set here on the first line. Right? I can create a sorted set variable on the second line, and I can store a reference to our tree set using that variable, right? Because a tree set is a sorted set. Right? Now, don't forget sorted set is also a set, right? So I can make a set variable here and also store a reference to tree in that variable, right? Because tree is a tree set, which is a sorted set, which is a set, right? And then finally, if you remember, all sets are actually, all implement the collection interface. So I can make a collection variable here and store a reference to a tree, right? Because trees are also collections, right? So the generic types, they work just fine in inheritance, right? You just have to remember that the inheritance doesn't work this way. Oh, sorry. All right. So if you actually have been poking around in the documentation for a lot of the standard library classes, especially the ones that involve generics, you're going to run into this question mark, right? So the question mark shows up all over the place. If you look in the class Java util collections with an S, right? Those are the utility methods that operate on lists and sets, right? Inside many of those methods, the generic types all typically involve this question mark character, right? And so just to be able to read the documentation, you need to understand what this question mark means, right? So the question mark is called a wildcard, right? And it's used in generic code to indicate that you don't know or you don't care what the generic type actually is, right? You have a generic object of some kind, like a list. You don't care what the element type is stored in that list, right? So when on its own, right? So if you just see the question mark on its own with nothing after it, right? Then the question mark is what's called an unbounded wildcard, right? It literally means we don't know what the type is, right? You might wonder why this would be useful, right? So it's useful when the type doesn't actually matter. For example, so we were talking, when we talked about generic methods, right, we had this method called clear, right, which would take a stack. Actually, I missed I should have included the original version here, sorry. So the original version of this method was generic, right? We had the angled brackets and a T here, and we had a T in here, right? For the clear method, all it does is pop the elements off the stack. It doesn't do anything with the elements. Right? So the actual element type doesn't matter, right? And so if you wanted to, instead of writing the method as a generic method with some type T, right, you can use the question mark instead, right? And so this tells everybody that's using the method that the actual type of the element in the stack is unimportant in this method, right? So when you use the question mark, it's not really for your benefit. Right? It's for the benefit of people who are going to use your methods and classes, right? And so when you see the question mark here, right, that indicates to you that, oh, the type doesn't matter in this particular method, right? Stack's generic, but the element type never plays a role in this method, right? When you actually look at the implementation of the method, right, nowhere do we ever use the element that's popped off the stack, so we actually don't care about its type. Right. So there's another way, there's another use for an unbounded wildcard, right? And so that's in a generic method where the only methods you use come from the class big O object, Right? Now again, in Java, this means that the type doesn't matter because all reference types in Java are objects. Right? So this is basically saying the same thing. Oh, sorry. Okay, so there's clear. Right? Now here's clear and print. So it's basically the same method. Well, it is the same method. The only thing, the only difference is I'm going to print the elements that are popped off the stack. Right? So while the stack is not empty, pop the stack. Right? Now here, I actually need the element. Right? Because I want to call toString on the element. Right? But generics, you can only allow reference types. Right? So whatever I pop off the stack, I know it's substitutable for object. Right? So I can take the popped element off, store it in an object reference, and then I can print the object using printline. Right? I guess here it would have been a little bit clearer if I wrote O2string. Right? Because you can call toString on any big O object. Right? So again here, the actual element type doesn't matter. Right? I know that whatever the type is here must have a toString method, so I can use it right there without any issues. Okay, so the unbounded wildcard on its own isn't super useful, right? It's, in other words, so it's only useful in some limited cases, right? What's far more useful is what's called an upper bounded and a lower bounded wildcard. Right? So you use an upper bounded so an upper bounded wildcard is similar to an upper bounded generic type, right? You're going to use this thing when you want to relax the requirements on a type parameter. Right? So consider the following method. So the next method I'm about to show you only works if you give it a list of number. Right? So here we've got the method sum of. Oh, this method should be, no, this is fine. Right? So here we have the method sum of. Right? It requires you to pass in a list of number because inside the method we're going to get the value of each element, the numeric value of each element, and add it to a sum. Right? So I'm going to start with the variable sum, right? And then write a little loop, right? So for each number n in the list t, right? Now you haven't actually seen the number class in any detail yet. So the number class has this method called double value. That returns the double value of any number, right? Of any number object n, right? And again, just quickly to remind you, the number class is the superclass of all of the numeric wrapper types. Right, so so this list of number, you could store a big I integer or a big D double or a big C character or a big S short or whatever other type of number type you want in the list. Right, so you can always get the double value of a number and you can add it to the sum and then you can return the sum. The problem here is though, you can only pass it a list of number. Right? If you tried to pass it a list of integer, that doesn't work, right? Because generic types aren't covariant, right? So they're invariant. Right? So a list of integer is not a list of number, right? A list of double is not a list of number. And so now I'm stuck, right? If I have a list of integer and I want to sum its values, I have to write a separate method, right? The better solution is to say, look, I don't want just a list of number. I want a list of anything, of any element type that's substitutable for number, right? So in other words, I want a list of something that is a subclass of number, and I want that to work, right? So that's what the upper bounded wildcard is for. So using an upper bounded wildcard, I can get this method to work for a list of any type, where that type is a subtype of number. Whoa. Like so. Right? And so just like an upper bounded generic type, the syntax is almost exactly the same. Right? The only thing that changes is instead of the letter T or E or K or something like that, this is now the question mark. Right? And so this says that question mark extends number. So what that means is it's a list of any type. Right? So that's what the question mark means, right? It can be any type, I don't care, as long as that type is a subclass of number. Right? And now this method works if I pass it, if I have a list of integer, it's fine, it works. If I have a list of double, it works. If I have a list of character, it works. If I have a list of long, it works, right? Because all of those types, right, are substitutable for number, right? And so the upper bounded wildcard lets you relax the constraint, right, that the element type must be number, right? Now you're saying it can be number, or anything that's substitutable for number, right? And that's how you get around the problem of of the fact that generic types are invariant in Java. Right? Now you might say, look, why did I write it this way, right? We already know how to put an upper bound on a generic type, right? So if I made that t, right, isn't that the same thing, right? So the answer is yes, it's basically the same thing, right? So I could have written it like that, right? That's fine, right? So there's my generic type. I've introduced a generic type, so I need to put the type in front of the return type for a generic method, right? But notice here, just like in the previous examples using the wildcard, the name t, big T, is never used inside the method. Right? So in other words, that type doesn't actually matter, right? And that's what the question mark is meant to convey, right? So for the person implementing the method, the question mark doesn't really help, right? For most people, well, I don't know about most people. For people who see generics for the first time, right, this is probably slightly easier to write, right? But for people who are using the class, right, that type name just gets in the way, right? It's totally unimportant to this method, right? And so the advice, or the recommended advice, is to use the wildcard here. All right, so an upper bounded wildcard, have we done this sub? Oh, right. So exactly what does this upper bounded wildcard do? Well, it restricts the unknown type to be, right, either exactly the same type as the upper bound, right? So for this method here, I can pass in a list of number, right? So that question mark can in fact be number, right? Or it can be any subtype of the upper bound, right? And so back here again, right? That question mark could be double, big D double, or big I integer, or so on and so on and so forth. Okay, so there's an easy way to determine whether or not you want to use or whether or not you might consider using an upper bounded wildcard, right? So you should consider using an upper bounded wildcard when your variable is a source of data, right? So look in this method here, right? This list T, right? I'm going to take the elements out of T and do something with them, right? So so this list T is a source of information for this method, right? I want to do something with the elements of T, right? And so now it's potentially useful to make this an upper bounded wildcard, right? So remember we were talking about our generic methods. We had this pop all method, right? And so pop all, it turns out, would be more useful if we had used an upper bounded wildcard, right? So back when we had our stacks class, right, where we were implementing these generic methods, right, we had a pop all method, right? So pop all took a stack called source, right, and pushed the elements onto a collection called dest, right? When we first implemented the method, right, the generic types were exactly the same, right? So if I have a stack of integer, right, I could push those elements onto a list of integer, right? If I had a stack of double, I could push those elements onto a list of double, right? But if I had a list of number and I had a stack of integer, right, this method doesn't work, right? Because T here is integer, right? That element type here is number, and they don't match, right? But the signature for the method says that they must match, right? They're both T. So they must have the exact same type, right? But if I have a stack of integers, I should be able to push those integers onto a list of numbers, right? So in this case, it makes sense to do the following. Right? So in this method here, oh sorry, let me back up here. In this method here, src, right, is a source of data. Right? I'm taking the elements from source and adding them to another collection. Right? I'm getting the elements by popping the stack. Right? If I change the method so that I say that this stack can be any type, as long as that type extends T, right, or as long as that type is a subclass of T, right, now this method works. Right? So if I have a stack of integer, right, and my collection is a collection of number, that's fine, right? Because integer extends number, right? And now this method works, right? So I no longer have that constraint where the types must be exactly the same, right? And this is exactly what the upper bounded wildcard is for. It lets you relax the constraints on type. So if you have an upper bounded wildcard, can you also have a lower bounded wildcard? And the answer is yes. Right? So a lower bounded wildcard restricts the unknown type to be, right, either the exact same type as the lower bound or a super type of the lower bound. Right? So remember upper bounded wildcard? The unknown type can be a subtype of the upper bound. Right? The lower bound lets you say that your unknown type can be a super type of the lower bound. Right? So if you wanted to find a lower bound, you use the keyword super instead of extends. Right? So again, the super keyword gets recycled. Right? It's now the third use of super. The third use of super in the language. Right? So just to quickly remind you what super is used for in the language. Right? So super in a constructor, on the first line of a constructor, is used to call the superclass constructor. Right? When you're overriding a method, super is used to call the overridden version of the method. And now it's used to define a lower bound in a generic type. Right? Okay, so here's a method called add1. Right? So add1 takes in a list of integer, right? And it adds the number 1 to that list of integer. Right? So it's pretty easy to implement, right? You just write t.add, and then you make an integer whose value is 1, right? And you add that integer to the list, right? Now, just like in the previous example, right? If I pass in, I can't pass in a list of number here, right? Even though I can add the number 1 to a list of number, right? Or if this was a list of object, right? That doesn't work either, right? Even though I can add any element to a list of object, right? And it doesn't work because the method says this must be a list of integer, right? But if you use a lower bounded wildcard, you can get the method to work, right? So it would be more flexible if you used a lower bounded wildcard instead, right? So like so, right? So I'm going to create a lower bounded wildcard, so question mark super integer. Right? So this says that the type here can be anything, right? So that's what the question mark says, right? As long as that type is a superclass of integer, right? And so this method works as long as that type is either an integer, big N number, or big O object, right? Because that's the inheritance hierarchy for integer, right? Object at the top, number in the middle, integer at the bottom. And so now if I pass in a list of object, that method works, right? If I pass in a list of number, it works. And if I pass in a list of integer, it also works. Okay, so notice the difference here between this method, right, where we're using a lower bounded wildcard, and here, where we're using an upper bounded wildcard. Right? So in popall, the type that has the upper bounded wildcard is a source of data. Right? So in this method here, we're doing something with the elements from the source. Right? And then we're going to add them to the destination. Here, when we're using the lower bounded wildcard, T, that list T, is not a source of data. Right? Instead, it's a sink or a destination for the data, right? So, oops, where'd it go? So lower bounded wildcards are useful when the variable is a destination for the data, right? And so there's another example of this. So push all is a method where we have a collection and we add the elements from a stack into that collection, right? So push all, did I do this right? Push all, no, I got these wrong, sorry. Destination push, oh no, I'm sorry, this is right. Okay, so in push all, we have a collection of elements of type T, right? And we're going to add those elements onto the top of a stack called dest. Right. So in our original version of the method, right, the generic types here and here are exactly the same, right? It's easy to implement. You just iterate over the collection, right? Push each element onto the stack, right? Now here, destination is a source, or sorry, is the destination for the data, right? So if I change, if I change that, wait, let me back up here. Okay, so just like in the previous example, right? If I have a collection of integer and a stack of object, I can't call this method the way it's written, right? Because integer is not the same as object, right? These types must match exactly, right? But if I relax, or if I use a lower bounded wildcard here to say that your stack type can be anything as long as a superclass of T, then that's fine, right? So now if I have a collection of integer, right, I can push the elements from source onto a stack where this type could be integer, it could be number, or it could be object, right? Because number is a superclass of integer, and object is a superclass of integer, right? And so now this method works for many more types for the destination stack type. Okay, so lower bounded wildcards are useful in generic methods that require a type to be comparable, right? So here's your binary search method from the collections class. Wow, what are they doing out there? Okay, so binary search. So binary search searches a list for some element called the key, right? And it uses the binary search algorithm to do so, right? So looks at the middle element, decides which side of the list that the element must be in, right? And then repeats the process, right? In order to decide which side of the list to look in, it needs to call compare to, right? So your element type in your list has to be comparable, right? I really should have introduced another slide here. Give me just 1 second here. I'm going to quickly make a separate copy of this slide. Okay, let me just fix this up here. Boom, boom. Okay. Okay, so back in an earlier slide, when I was talking about the sorted minimap, I said that you could impose the constraint, right? That your element, that your element type T must implement the comparable T interface, right? But this turns out to be too restrictive, right? So the problem is, imagine that, so remember our counter class, right? So the counter class implements comparable counter, right? So I can compare all counters to other counters by comparing their value, right? And then we subclass counter, right? So we made a stopping counter subclass, right? But we never replaced the implementation of compare to, right? And so our stopping counter also implements comparable counter, right? It doesn't implement comparable stopping counter, right? You can compare a stopping counter to any kind of counter. So the problem is if you wrote binary search this way, if you had a list of counters, right, you can't look for a stopping counter in that, sorry, other way around, right? If you had a list of stopping counters, right, you can't look for any particular counter in that, sorry, yeah, that's correct. Wait, hold on, just 1 second here. Do I have any super type? Right. If I had a list of counters, I can't look for a stopping counter in that list, right? Even though stopping counter implements comparable counter, right? Why? Because the types are all the same. There's T, there's T, there's T, right? So if T is stopping counter, I can't search a list of counter, right? So that's no good, right? So what I really want is I want to be able to search a list of, sorry, any counter type, right? As long as that counter type implements, comparable, where I can compare that type, right? So here, right, if T is stopping counter, right, then I can have a list of anything as long as it implements comparable to some supertype of stopping counter, right? So if the type here is counter, that's fine, right? Counter is a supertype of stopping counter, so I can now search a list of counters for a stopping counter object, right? And that works just fine, right? So here, the lower bounded type on comparable lets you search collections where only the supertype implements compare to, right? And the subtypes don't, right? So this is exactly the way that binary search is written in the standard library, right? And it's written this way so that it works, so this particular method works when you're trying to search objects that are part of an inheritance hierarchy. All right, so that's, so that you basically know, you know everything you need to know about generics. You know, so you basically know almost everything there is to know about generics at this point in time, right? So if you go back and review this lecture slide and you actually understand, sorry, not this lecture slide, this set of slides, and you understand what's going on, you can now go and actually look at the documentation for all of the standard library classes, and you can now actually make sense of this gobbledygook, right? So if I had shown you this in like week 3 of the course, right, you wouldn't know, most of you wouldn't have any idea what the heck's going on, right? At this point now, right, at least you have a chance of understanding what's going on, right? I'm not saying you actually will be able to decipher all of these things always, right? But at least you have the basics of understanding what exactly is going on when you see stuff that looks like this, right? Hopefully you also understand why stuff like this is necessary, right? All right, any questions? Okay, this is not the easiest stuff to understand. So, I mean, if you don't really, if you're a little bit confused about what's going on, don't be surprised. It does take a while for this to all sink in and for you to understand actually what's going on. All right, so that's all I want to talk about today. Sometime either Thursday or Friday, I'm going to hand back your test 2. And then I guess next week we'll wrap things up in the course. All right, thanks everybody.